My name is Benjamin Andrews, and this is Team 37 Design Phase 3. So patents were analyzed to generate ideas. This is the analysis of intellectual property, where the team conducted research on 5 patents for different types of automated pet feeders and incorporated the ideas of some of these into some of our concept designs. So the first one had a tapered food hopper and rotated dispensing food as it rotated. So we incorporated the idea of rotating food storage into some of our concepts. The second one was gravity induced. So we incorporated the idea of gravity food delivery into most of our concepts, and this one also incorporated water, which we had in most of our concepts as well. The third one had separate food and water storage and incorporates water, so that's what we incorporated into some of our concepts. And the fourth one had a programmable food release and sectioned food storage, and the programmable food release is something that we incorporated into all of our concepts, and sectioned food storage was incorporated into some of them. And this one had a USB where you program it from, and that was incorporated into our final design. And the final one had a motor-powered food release and section food storage, and motor-powered food release was incorporated into all of our designs. So this is a concept combination table that was created based on ideas generated both internally and from the analysis of intellectual property. And as you can see on the table, some of the things incorporated from intellectual property, such as rotation for food dispense, free fall based gravity, and user input from a computer where you program it through the USB. And you can also see different ideas that were generated internally by the team, such as solar panel for power and different installation options, which were not discussed in any of the patents that were researched. So the team used several processes to determine a final design, such as concept screening, concept scoring, and the gallery method. And concept screening and scoring tables were generated through incorporating the ideas gathered from the gallery method. And the concept screening was discussed as well as the gallery method in DP2 in detail, so we're not going to go too much into that. But this is our concept scoring table, which after the concept screening, which eliminated 2 of our potential solutions based on just they were not feasible. This is how we determined to move forward with our final solution, which is solution 4, which we'll see on the next slide. And we decided this based on the selection criteria seen here, which was established based on interviewing of customers and establishment of customer needs. And we assigned the weight based on how frequently the customers spoke of this in the customer interviews. And we assigned the rating for how effectively each solution accomplished the task internally. So we calculated all of these, and the one with the highest score is what we'd move on with, and that was solution 4. So that's the one we moved on with in the end to proceed to our prototype. And this is the final concept decided on by concept scoring. As you can see, it incorporates gravity food and water, and a button panel, and notification LEDs that let the user know if you need to change the water, the food, the battery, and so on. So in the final design, as you'll see, we had to get rid of some of these features due to just time constraints and the feasibility of incorporating some of these features. And failure modes and effects analysis was conducted to determine the areas of improvement based on the probable failures and the severity of the failures. So the team generated different potential failures, such as a failure in food release where no food is released at all, and we ranked them based on severity, occurrence, and detection, and gave them an RPN, and the one with the highest RPN is the most severe of the failures. So of all of them, the most severe was a failure to release food at all, which would result in pet death, which had an RPN of 96, which is the highest, meaning it's the most severe. And the recommended actions to prevent this would be a fail-safe mechanism or improved food delivery. So the second error the team came up with was too much food release, which would also be a failure in the delivery mechanism. And the solution to that was a more precise feeding mechanism as well, but it only had an RPN of 60, making it the third most severe error that we established. And the last one, or the third one, would be the feeder would either fall off where it's attached, or if it's freestanding, it would fall over, and that would cause potential break of the feeder altogether, or it could injure a pet, and that would be caused by an installation error and would be detected. You could just visually see when it happens. And this only had an RPN of 18 because it's not that common and not that severe. And the recommended solution would be an increased stability of a freestanding feeder or increased fastener strength if it were fastened on a cage. And the final one would be clogged food release, which too little food would come out, which would cause a motor malfunction. And this is also detectable visually. It had an RPM of 75, meaning it's the second highest, most severe failure. And the improvement to that would be an improved delivery mechanism. So the team created models for the prototype in CAD. And you can see this is the food delivery mechanism, which is basically just an elongated gear. So we made the gears as well as this in CAD and had them 3D printed for our final design. So here's our actual prototype constructed. You can see some deviations from the CAD model, such as this Arduino box, which was not part of the CAD, but we didn't have enough space and couldn't incorporate the Arduino box with the size of the box that we had. And you can see that we didn't actually have a LED touchscreen user interface because that's just not feasible for our current level of understanding of programming. So we just painted on and modeled it. And as you can see here, the internal of our actual prototype, which has the Arduino powering a gear train which rotates the food delivery mechanism. So the way this would work is you program the Arduino to spin a certain number of times a day and for a certain amount of time, and you program it the amount of time you want, which would cause this to rotate so you can get the desired amount of food release depending on how much you want to feed your pet. So next, the DFA was constructed to determine assembly time, which is how long it took the team to assemble the final prototype, and this is based on exactly how much time it took us to do everything, such as cutting all of the wood, 3D printing, and putting it all together. And as you can see, 51 minutes is a very, very long time and is not a good enough time for a mass-produced model. And you can see the time that had the longest amount of time it took us in the DFA was putting the actual box together, because we had to hot glue it and hold it in place and let it dry. And that was just a very lengthy process, and eliminating that would eliminate 27 minutes of the total time just in those two steps alone. Next, a bill of materials was constructed to determine cost, and this is just based on the materials we went out and bought and how much it costs. So we had to get a balsa wood sheet, which we cut all of our body for, and the ramp and the food ramps using the laser cutter, and that total cost was $729. And then 3D printed gears were free from the library, and then we had to get paint and paintbrushes to paint the LED screen because we couldn't feasibly incorporate that in the time that we had. And the total cost was $16.14, which differs from the cost in the economic analysis, which was $10. But a mass-produced model would most likely be a lot cheaper than this due to increased production time and production cost. So all of these analyses, such as DFA, bill of materials, and intellectual property, led us to these improvements that we would incorporate if we were to make a version 2.0. So these improvements decided upon were an improved production process, which would decrease time and cost, and this would incorporate most likely a injection molding for the entire body, that all the non-moving parts. So if you see here, the ramps and the actual body would all be injected molded at once, greatly reducing time and cost. We would find a way for a more precise food delivery mechanism to decrease some of the failures that were established in the feasibility and economic analysis. We would incorporate an increased stability of the feeder to decrease the possibility that it falls down or falls off the wall. We have increased fasteners and the ability to change what types of animals the feeder caters to. This is ultimately the major goal of the entire pet feeder, was to be able to use it for dogs.